Okay, so I'm going to now talk about orbital notation. So orbital notation is just ensuring that we see all of our numbers. It's showing us where the electrons are actually at in the orbital in a more visual way. So you can see that they do not spin in the same direction. One's spinning clockwise while the other one's spinning counterclockwise. So they're spinning in opposite directions, okay? So that being said, the first step is you just write your normal electron configuration. So I already have that first step done, normal electron configuration. The next step is talking about the orbitals. So if you remember, we have 4 different orbitals. We have s orbitals, p orbitals, d orbitals, and f orbitals. And so whenever we talked about the orientations, the 1, 3, 5, and 7, that's how many can exist at one time. So for s's, there's only one that can exist at a time. For p's, I won't go off camera and keep talking. Okay, sorry. So for S's, my balloons went away. There's only one orientation, so no matter how I rotate it, S is right here. If I tried to do another S balloon, they would collide. And so for each energy level, only one S can be on there. Okay, but for P's, remember we talked about how there can be 3 at any given time on that same energy level. So it's saying how many actually exist at one time. And so for P's, for S's, we only have 1 that can exist per energy level. For P's, we can have 3. For D's, we can have 5. And for F's, we can have 7. And so that's how many orbitals actually exist. And so we represent the orbitals with lines. So S's only have 1 orbital that can exist at a time, so we only write 1 line. So right here in the 1s, there's only 1 orbital there. 2s, there's only 1 orbital. P, we have 3 orbitals, so I give it 3 different lines. S, again, only 1 orbital. P, 3 different lines. Okay, and so now we have all of our orbitals represented by lines. And now we're going to fill those lines with electrons. We represent electrons with arrows. An up arrow for clockwise, and a down arrow for counterclockwise. I'm just going to write counter because I'm too lazy, okay? So we represent them with an up and a down arrow. Remember, at most, each orbital can only hold 2 electrons. So that means each of these p orbitals can only hold 2. So in total, we can have 6, 2 in this set, 2 in this set, and 2 in this set for this p orbital. And so the s's can only hold 2 as well, but there's only 1 of them. So each line represents an orbital. Each orbital can only hold 2, so each line can only have at most 2 arrows. Whenever we do this, if you remember Pauli exclusion principle, our last number says that each electron that occupies an orbital, if there's more than 1, they have to have opposite spin. So if you cannot have 2 up arrows or 2 down arrows, you have to have 1 up and 1 down, showing that one's going clockwise and one's going counterclockwise. So right here, I'm in the first energy level, s orbital, and I have 2 electrons in that s orbital. So that means this line needs 2 arrows because I have a little 2 right there. So I'm going to do an up arrow. I'm real lazy, I do half arrows, and I'm going to do a down arrow to show that one is going clockwise and one is going counterclockwise. That orbital is now full, and we know that because it matches 2 and 2. So we come over here. I'm in the second energy level now. I still have the s orbital, and so now I still have 2 electrons. So I'm going to do 2 arrows again. One to represent the first electron and one to represent the second one. One is spinning clockwise, one is spinning counterclockwise. My half arrows are the same thing as full arrows, it's just me being lazy. So now we come over here and now we're in the second energy level still. Now we have p orbitals, which means that we have 3 different lines because 3 different p's can exist at once. Remember my orange balloons. And in total we have 6. So that means that I need 6 arrows. So I'm going to go through and I'm going to give 1 arrow to each because we don't want to double up unless we have to. And then I have to double up, so I'm going to go back and give a second arrow to each one. Why don't we want to double up if we don't have to? Well, because electrons want their space. They don't like to be next to another electron because they're both negative and they're going to repel, and they really don't want to hang out together unless they absolutely have to. It's kind of like you. You don't want to hang out with your sibling more than likely unless you absolutely have to. So if you lived in a really big house where there were 3 rooms and you had only 1 other sibling, you don't want to share a room with your sibling when there's 2 empty rooms beside you. you're gonna want your own room and your sibling's gonna want their own room. Electrons are the same way. If there's an empty orbital, they want their own orbital. They don't wanna have to share their orbital unless they have to. Okay, we'll keep going because I'll show you that in a second. So now we're at the third energy level, the S, and we have 2 electrons, so I need 2 arrows again. One going up, one going down. And so if you can see this one had 6, 2, 4, 6. This one has 2. Over here, we have 3, we're in the third energy level, P's, and we have 3 electrons. So I have 3 orbitals and 3 electrons. So each orbital is just going to get 1 electron. And they're all going to be going up. We always do clockwise first just because that's what we naturally go to. And so we don't actually know which way they're spinning, but we just assume it's clockwise. But that being said, each one got their own room because remember, just like you and your siblings, you don't want to share. If you lived in a house with 3 empty rooms, there's 3 kids, each kid should get their own room. If there's 3 empty orbitals and there's 3 electrons, each electron should get their own orbital. So hopefully that makes sense. That's how you do orbital notation. If you have questions, let me know. I am available for tutoring. Y'all have a good day.